There are many real-life situations, especially in scientific studies, where we need to use very large or very small numbers. The age of the Earth is estimated to be 4.6 billion years. A beach could have more than 1 quadrillion grains of sand. That's a 1 followed by 15 zeros. And distances in space become, well, astronomical. 940 quadrillion kilometres across our Milky Way galaxy. And from the Milky Way to the Andromeda Galaxy, a staggering 20 quintillion kilometres, which is 20 followed by 18 zeros. With the rapid advancement in digital storage, there is also an ever-increasing need to use very large numbers in day-to-day life. A 1 terabyte hard drive has 1,000 billion, which is a trillion, bytes of data. One way to deal with such large values is to use the different prefixes, such as tera, giga, etc. Or we could use special naming conventions such as billion, trillion, and so on. You can watch the video on metric prefixes to learn more about these. In this video, we will see how scientific notation allows us to write any large number in a nice, succinct format. Equally, small values are also encountered, particularly in scientific studies. The width of a grain of sand, the weight of a dust particle, or the mass of an electron. Again, we could use metric prefixes or special fraction names such as billionth, but scientific notation still provides a concise way of representing very small numbers too. Before we delve further into scientific notation, let's revise the 3 main skills you will need. 1. You need to understand place value for our decimal base 10 number system. 2. We should know that multiplying or dividing by powers of 10 simply moves the position of the decimal point. And 3. We need to know how to write powers of 10. Looking at the expanded values and their matching powers of 10, we see, conveniently, that the power matches the number of zeros after the 1. This makes it very easy to change to and from positive powers of 10. For negative powers of 10, the negative sign can serve to remind you that you simply need to write the reciprocal of the positive power. In other words, we write it as a fraction with 1 over the same value as the positive case. So the number of zeros in the denominator still matches the power. When written in decimal form, with a 0 in front, then conveniently the number of zeros still matches the power of 10. Further, the number of decimal places also matches the power. Hopefully these little tricks will help you better understand how to write powers of 10 for both positive and negative powers. This is vital for changing numbers to and from scientific notation. The other important skill is to know how to multiply or divide any number by a power of 10 without using a calculator. We can do this simply by moving the decimal point, since our place value columns are based on powers of 10. We are making the number that many times larger or smaller, so we are really pushing all the digits into higher or lower place value columns. To calculate 6.145 multiplied by 100, which is really the same as multiplying by 10 squared, each digit goes into the column 2 place values higher, pushing all the digits 2 places left. Of course, we don't write a table showing the place value columns, so it looks like the decimal point has moved 2 places to the right. This is why we learn the simple trick: when multiplying by a power of 10, count the zeros or read the power of 10 and move the decimal point that many places to the right. If we run out of digits to jump, we simply fill in the extra places we jump with zeros. In this example, we are multiplying 2.1 by 1,000, which is the same as multiplying by 10 to the power of 3. So we jump the decimal point 3 places to the right, filling the empty spaces with these extra 2 zeros on the end. Knowing this, we don't need the table of values. We just move the decimal point the required number of places and fill in zeros if required. What value will this calculation give us? 1.75 multiplied by 100,000 has 5 zeros, so moving the decimal point 5 places to the right means we need 3 extra zeros after jumping the 7 and the 5. This is the very essence of scientific notation. Writing the product to include a power of 10, like this, is called scientific notation. The number out the front has to be less than 10 though, otherwise we could have included another power of 10. And for similar reasons, it cannot be less than 1, because this will subtract powers of 10. We can now define scientific notation as follows. A number is in scientific notation when written as a number from 1 up to, but not including 10, multiplied by a power of 10. Importantly, any decimal number can be written in this form, although its true advantage is to replace very large or very small numbers with this more succinct notation. Rounding is often required, as we will see later. It is important to be able to interchange between decimal form and standard form, which is scientific notation, especially in mathematical, scientific, and engineering fields. A convenient technique is color-coded in these last two examples. For numbers greater than 10, we write the non-zero digits out the front, although we might need to round or include extra zeros to indicate the correct level of accuracy. We place a decimal point after the first non-zero digit here. Then we count the number of digits between the new position of the decimal point and its original position, here, on the end of the number in this case. We find the decimal point has moved 24 places. This tells us the power of 10 required. It's a positive power because we need to move the decimal point to the right to put it back where it was. In other words, 9.23 is multiplied by 10 24 times to create the large number we started with. For the second example, we have a very small number. The original position of the decimal point was here, but now it's here. Counting the digits, we find that it has moved 16 places. We would need to move it 16 places left to put it back where it was. So the power of 10 is negative 16. You might like to pause the video and try these two yourself. You should immediately realize that the first number is more than 10, so its power of 10 will be positive, whereas the second one is less than 1, it's a decimal, so its power will be negative. Now we just need to figure out the values of the powers by counting the digits between the original position of the decimal point and its new position, which is always after the first digit that isn't a 0. Here, 17 digits this time, so our number, written in scientific notation, is 7.8401 multiplied by 10 to the power of 17. For our small number, we place the decimal point here after the 1. There are 10 digits in between, so the power is negative 10, giving us 1.050 multiplied by 10 to the power of negative 10. Notice that I kept the extra 0 from the end of the decimal. Extra zeros on the end of a decimal are clearly showing you more information about how precise the value is. We might elect to keep extra zeros for the large number case as well, if we also want to show more precision. To fully appreciate why and how we determine the number of digits to keep, you need to understand significant figures, which I discuss in this video of the same name. In summary though, the number of digits you keep out the front here must match the number of significant figures you require. We won't focus too much on this in this video. Before summarizing and practicing with some more examples, let's take a closer look at why this process works for negative powers. Consider 0.021, which can be written as 2.1 divided by 100. This can also be written as 2.1 divided by 10 squared. which is similar to scientific notation but has a division instead of a multiplication. Scientific notation requires the number to be multiplied by a power of 10 for consistency and because it has been defined this way. Well, dividing by a number is identical to multiplying by its reciprocal. For example, multiplying by 1/2 is the same as dividing by 2. So dividing by 10 squared is the same as multiplying by 1/10 squared, like this. Finally, 1/10 squared is the same as 10 to the power of -2, as discussed earlier. Now we can summarize the simple steps to follow for changing any number into scientific notation form. I will complete these two examples as we go. First, we move the decimal point to follow the first non-zero digit. This always gives us a value greater than or equal to 1 but less than 10. In our examples, we get 7.39 in both cases. Then we count up the number of places we have moved the decimal point. The easy way to do this is to count the number of digits between its original position and its new position. Counting the digits between these two positions tells us the power of 10. In both our examples, we have moved 8 places, to the left in the first one and to the right in the second. To determine the sign of the power, simply look at the original number. If it was greater than 10, the power is positive. If it was less than 1, the power is negative. There is one case our summary doesn't cover, when the number is less than 10 but not less than 1. For example, 7.39. In cases like this, the decimal point is already after the first non-zero digit, meaning it does not have to move any places at all. Writing it in scientific notation means the power of 10 is 0, like this. Of course, there is no benefit in doing this. Remember, scientific notation is intended for very large or very small numbers. By the way, 10 to the power of 0 is equal to 1. So we really have just multiplied 7.39 by 1. Let's practice with some more examples. Pause the video if you'd like to try them on your own first. Number 1 is hopefully obvious because we see 7 zeros after the 2, meaning it is 2 multiplied by 10 to the power of 7. If it wasn't obvious, then following the steps we would move the decimal point from the end of the number to follow after the 2. Then, counting the digits between these two positions gives us 7 for our power of 10. Remember, we could also write 2.0 or 2.00, etc. if we needed to show that the value is more precise. In number 2, we move the decimal point from here to here, telling us the power of 10 is 5. So our answer is 3.74 multiplied by 10 to the power of 5. I won't keep adding zeros for every example, just keep it in mind when greater precision is required. In example 3, we move the decimal point from here to here 11 places, giving this answer. In this example, our answer might be too precise, and we could round to something more suitable, such as 2.5 times 10 to the power of 11. Next, after moving the decimal point, we count only 3 places, resulting in 8.3516 multiplied by 10 to the power of 3. For number 5, 90 is only 9 lots of 10, which means 10 to the power of 1. There is no real benefit in writing 90 in scientific notation. The rest of our examples are all numbers less than 1, so we immediately know all their powers will be negative. For number 6, we move the decimal point to be after the 5, a total of 4 places, so the power must be negative 4. We have 5.1 times 10 to the negative 4. Next, we have only one place to move the decimal point, so 0.3 is the same as 3 times 10 to the power of negative 1. And in the last one, we need to move 10 places to jump over the 9, so the power is negative 10. Giving us 9.504 times 10 to the minus 10. Now let's see how we can change numbers presented in scientific notation back into decimal form. Naturally, we need to do the process in reverse, putting the zeros back in place as we go. For positive powers of 10, as we saw earlier in the video, the power tells us how many places right to move the decimal point, and negative powers mean move it left. In both cases, if we run out of digits to jump, we fill in with zeros. Pause again if you'd like to try these examples on your own. In the first, we need to move 5 places right. After jumping the 0 and the 1, we need 3 more, so we fill in with 3 zeros, giving us 301,000. In number 2, the decimal point isn't shown, which means it's at the end of the whole number. We need to jump 9 places to the right, so we simply add 9 zeros. In the third example, we need to jump 2 digits. There are 3 available, so our decimal point ends up after the 7. We should still show the last 0 because it provides extra information about how precise this value is. The final 3 examples all have negative powers, so the decimal point will move to the left. For negative powers, you will always fill zeros after jumping the first digit, since there will always be only one digit in front of the decimal point when written in scientific notation. This provides a convenient shortcut. Ignoring the negative, the power tells us how many zeros to write in front, and then we simply place a decimal point after the first 0. In example 4, we need to move the decimal point 5 places left, so we write 5 leading zeros and place the decimal point after the first one. Next, we only need to move 1 decimal place, so we jump the 8. We still like to place 1 0 out front. In the last one, we write 11 zeros in front of the 9, 10 of which will be after the decimal point. This example illustrates why scientific notation is so useful. It's often so much shorter to write. Imagine if there were 20 or even 30 zeros after the decimal point. To wrap up this video, we will see how to use scientific notation on a calculator, and even how it can change a number into scientific notation for you. On most modern calculators, like this Casio model, the required key for entering values in scientific notation is quite obvious, as we see here. And the display, especially in the final result, is also clearly in scientific notation form, as seen here on this calculator screen. This isn't always the case, especially on older models like this one. Firstly, the button for entering such values is not obvious. It's this button here. The EXP stands for exponent or exponential form, reminding the user to write the decimal part and the exponent part, the power of 10, separately, separated by tapping the EXP button in between. Notice this small 18. It looks like it could mean the number is raised to the power of 18. This display actually means 3.84951 multiplied by 10 to the power of 18. I won't show any more on these older models. Be sure to refer to your user manual if yours is similar to this one. Let's start by entering 3.15 times 10 to the power of 7, assuming you have a similar calculator to this Casio. Be aware some current models might still label the key as EXP despite it displaying the entire notation. There are 2 ways to enter this value, with or without that special button. Type 3.15, then press the times 10 to the power of X key. The calculator is now waiting for the power of 10, so simply type 7. That's it. Alternatively, you can type exactly what you see. 3.15, then the multiplication key, followed by 10, then press the power key, and finally type in the power. Using either method, then pressing equals, will usually convert the answer to decimal form, if it can fit on the calculator's display. Otherwise, it leaves it in scientific notation. If I change the power to 17 instead of 10, we see that it no longer converts to decimal form, since the required number of digits will not fit on the calculator screen. An important point: be careful not to use both methods at once, or you'll end up with an extra power of 10. On calculators like the Casio, though, it's very obvious, as we see here. However, it is a real problem on calculators with the EXP button, as students often type times 10 followed by the EXP, which gives them an extra power of 10. Now let's go back and make the power a -7 using the sign change key here. Your calculator might have a plus/minus key instead. You might get scientific notation like this, or a fraction, or a decimal. It is often possible to choose the default display. Check your calculator manual. In a Casio, press Shift, then Setup, then 8. We are then given two options for our normal display. Type 1 will give small decimals in scientific notation form, as seen here. Type 2 gives either the fraction or decimal, which we can then alternate between using the SD key. I recommend type 2 for most students. And last of all, we look at a special mode that changes all your answers into scientific notation. This can be useful if you want to keep everything in standard form. You go to Shift, Setup, or equivalent on your calculator. Can you see anything that might suggest scientific notation? So we press 7. Now it's asking you how many significant figures you wish included. If you haven't yet studied significant figures, don't worry. It simply decides how many digits to keep out the front. It's probably best to select 9 because you can easily discard extra zeros if you wish to do so. However, if you select 3, for example, then all answers will be rounded to only have 3 digits out the front, and you could lose some detail or precision depending on the calculations. Take care when using this mode because you might inadvertently give a rounded answer. When you have finished, remember to go back and reset your calculator to normal type 2.